Hi there, once again, grade 12s. It's Physical Sciences on Mindset. My name is Tinyiko Kosa. I welcome you again. We are going to continue doing some revision of some crucial work that comes from grade 11, but still very important and applicable at grade 12. Now today, we will be talking about electricity and magnetism. Now, so that is the topic for today. We will be focusing mainly on electrostatics. And as I will explain later, I think you also remember what electrostatics is all about. That is electricity, that is stationary or studying charges that are not moving, static electricity. We are going to look at units that are used when we deal with electrostatics. We will definitely be talking a lot about Coulomb's law. We will also have a look at electric fields and electric field strength. So those are the sections of work that we'll be looking at in this particular lesson. Now let's start by going back to some of the things that we even did at grade 10. When we work out solutions to problems in electricity and even in other sections, we need to know the units that we're dealing with. Now, in electrostatics, basically, we deal with units that sometimes are so small, but then we need to convert to SI units. Now, these small units have got prefixes, and those prefixes are things like milli, micro, nano, pico, femto. And you will see that we don't really talk much about this one, but it does exist. And with milli, micro, nano, and pico, we come across these ones more often. Now, the symbol for milli there will be that small m there. For micro, we use that mu, that sign there for mu, and we also use N for nano, we use P for pico, and F for femto. Now, what is crucial is the factor that is brought in by this small units when we're dealing with our units. You would see that the values are so small. Let's talk about milli. When we start with milli, you see we've got 10 to the power 3. This means that if you are to convert from something that says milli, say millicoulombs, all right? Millicoulombs would mean that to move from millicoulombs to coulombs, you need to multiply by that factor there. In the same way, when we talk micro, the factor or the value of that is 10 to the power minus 6. So if something is given to you as microcoulombs, to move on to coulombs, it means you will have to multiply by this factor here. In the same way, we have the nano, and the symbol is N, and for this one, you'll have to convert by multiplying by 10 to the power 9, minus 9. Pico, on the other hand, will have a value of 10 to minus 12. And if you're talking femto, you will have a value of 10 to minus 15. So that's how we're going to do our conversions. We will have a short exercise in which we will be making use of these units to do our conversions from the small units to bigger units, or to SI units. Let me put it that way, actually. We convert from the units that are given to us such that we can work in the SI units. Now, what are SI units? The word SI stands for System International. These are units that are commonly used worldwide, so that a scientist in South Africa, talking in terms of measurement, should make sense to a scientist sitting anywhere around the globe. Now, let's look at some of these conversions that we need to do. Say you are to work with nanocoulomb. That's 5 nanocoulombs. We know that in terms of charge, we make use, the unit that we use to measure charge is of course the coulomb, which is given in honor of the scientist that did a lot of work around charges, and his name was Coulomb. And now, if it's nanocoulomb, if we go back to our table, nano, it's 10 to the power minus 9. So if I am to convert here, it means 5 nanocoulomb will be the same as 5 times 10 to the power minus 9 coulombs. Now this is what I will work with. I don't have anything to do more from here by still converting, because this 5, you would see it's a number between 0 and 10. Now, if you go back to grade 10, learning about how to write your numbers in scientific notation, you would remember that you're writing numbers as digits between 0 and 10 and expressing them as powers of 10. So that is good enough in converting your units in this case. Next, we have 1,5 microcoulombs. Now micro, let's look at micro. Micro, it's 10 to minus 6. Now, this would be 1.5 times 10 to the power minus 6 coulombs. Now, in the same way, that's enough in converting these units. Now, let's come to something else. This is now farads. 2 farads, 2 picofarads. Now, pico is 10 to the power minus 12. So thus, to convert it to the SI unit, which will be farads, it will be 2 by 10 to the power minus 12 farads. Let's come to this one, a nice one. It says 0.2 millivolts. Now 0.2, it's 0.2, a number between 0 and 10. Yes, you can say so, it's a decimal number, but it's a fraction. Another thing that we can talk about here in terms of scientific notation is that we are saying it has to be digits between 0 and 10. Now 1, 2, 3, 4, 5 between 0 and 10. Now 0.2 gives us a bit of a problem because it's not just a single digit there, it's a decimal fraction. So what we'll do is that we'll say, okay, this is 0.2 times 10 to the power milli. You can go back to your table. Milli is 10 to the power minus 3, and therefore this will be to minus 3 volts. Now we have a bit of a problem here because we also want to make sure that we honor that rule, the scientific notation. So we would want this to be written as 2, so we're moving our comma to the right. So you will agree with me that 0.2, if we want to take this comma to that point, it means I would have multiplied this by 10 so that I have now, instead of 0.2, I've got 2 as a digit there. Now, this is 10 to the power 1, so if I had 2 by 10 to the power 1, by 10 to minus 3, the resulting answer will be 10 to the power minus 2 volts. Now, that's how you could have converted that particular one in this case. Now, that's a simple exercise on how to convert from the units in which you are given data to the SI units in which you are required to use when you do your calculations. It's very important. Now let's come now straight to one of the main sections of this lesson, which is Coulomb's law. Coulomb's law. Let's state it. The law says the electrostatic force between any 2-point charges is directly proportional. Now we're talking relationships here. Directly proportional to the product of the charges. And again, the same electrostatic force between the two charges is inversely proportional to the square of the distance between them. Square of the distance between them. Now we can take this law or work on it from section to section. But allow me to just write it down here mathematically. At the end of it, we will be coming to that law there, which is called Coulomb's law. Now, I've already said that this law is about relationships. Let's unpack this law in terms of the relationships that are given to us. We are told that the electrostatic force that exists between any two charged objects, this force is directly proportional to the product of the two charges. So this force that exists between any two charged objects is directly proportional to the product of the two charges. So if the two charges are represented by charge 1, Q1, and Q2, charge 2, then this force is directly proportional to the product. This means you are multiplying Q1 by Q2. Remember that a product is an answer that you get when you multiply. So force, or the electrostatic force, is directly proportional to Q1 times Q2. That's the first relationship that we are getting here. Very important. Let's look at the second part of the relationship given in our Coulomb's law. It says the electrostatic force that we're talking about, the very same one, is inversely proportional to the square of the distance between the two charges, or the two charged objects. So the same force, F, is inversely proportional. Now, for an inverse proportional relationship to be represented, we make use of the reciprocal. So this will be 1 over what the force is inversely proportional to, which is the distance, the square of the distance between the charges. We make use of small r to represent the distance between the charges. So if the charges are here, Q1, Q2 is there, the distance we are referring to is the distance as taken from the center of the two objects that are charged. So that will be our r. So that is the r square that we're talking about. Remember, it says to the inversely proportional to the square of the distance between them. Don't forget that. It's very, very important. Now, Coulomb's law equation, like I've written it already at the beginning, you would see that the two relationships are now put together here. The two relationships, which is F being directly proportional to the product of the charges. Now, to be consistent with what I have here, I'm going to use small q for now. Then it will be Q1 times Q2 divided by r squared. That's when you have put together the two relationships. So this electrostatic force here, this electrostatic force here, is proportional to Q1, Q2 divided by r squared. For us to remove the proportionality sign, we bring in a constant called K. And when we do that, bringing down K, we remove the proportionality sign and we replace it by the equal sign. Therefore, the electrostatic force F will be given by K, Q1 times Q2 divided by r squared. And the value of k, which is a constant, is given as 9 by 10 to the power 9 Newton meter squared per Coulomb squared. That is the value of k that we're going to use in calculations when we make use of Coulomb's law. Now, there's something I want you to remember as we talk about the force, this electrostatic force between any two charged objects. Remember that in lesson number 1, when we were talking about mechanics and we're talking about force resulting in motion, we actually brought in the idea that physical quantities can be classified into two. We have got those that are vectors, we have got those that are scalar quantities. And we said that force is a vector quantity. In the same way, the force that we're talking about here, this electrostatic force, remember that it is a vector. So in other words, direction becomes very important when we talk about this electrostatic force, because how did we define a vector quantity? We said a vector quantity, it's a quantity that has got both magnitude and direction. So vector has both magnitude, how big the quantity is, plus direction. So we need to be aware that we're talking about force, and force is a vector quantity. So direction becomes important. Like charges, this is another thing that you need to remember, because that is where we get our direction of an electrostatic force. We need to know that like charges repel each other, and unlike charges attract each other. This is where we get our direction. What we mean by this, I need to go back to it to show you a little bit about charges. When we talk like charges, remember we've got two types of charges. We've got negative and positive charges. Negative represented in that way, and positive charges. And that represents positive charge. When we say like charges repel each other, we are saying if you put a negative charge to a negative charge, we will have repulsion. So these objects that are negatively charged, when brought to each other, they will repel each other. In the same way, if you put positive to positive, we will have repulsion. So that is the like charges repelling each other. But on the other hand, if we have a negatively charged object brought closer to a positively charged object, what we will see is attraction. So whichever objects that you have brought together with different charge, with opposing charges, positive and negative, these objects are going to draw near to each other. They will be pulled towards each other because unlike charges attract each other. So that is basically what we're talking about. And remember, this is where the direction of an electrostatic force comes in. So when we calculate for an electrostatic force, we should be able to say at the end that there will be this object which is negatively charged and this one which is positively charged. The negatively charged object will move towards the positively charged, or the positively charged object will be moving towards the negatively charged. But know that both processes are actually happening at the same time. But if the objects are carrying the same charge, they are going to repel each other. In other words, they are going to be pushing each other. They are going to be pushing away from each other. One object will be pushing the other away from itself. So that's what is going to happen. And that's how we're going to illustrate our direction. Now let's quickly have a look at an example. Example 2. We've got two small identical spheres. Identical means they are the same in all respects. These two spheres are suspended by a long silk thread, or long silk threads, and they are free to move as shown in the diagram here. So they can move, and because firstly we can see this one is positively charged and that one is negatively charged, so we expect them to be moving towards each other. They should be attracting each other. So we are also told that the charge carried by these spheres, this one has got a charge of +2 microcoulombs. So we are given charge in microcoulombs. This one has got a -6 microcoulombs. Now, in our calculations, we cannot use microcoulombs. We need to use coulombs, which is given the symbol C. So we need to convert from microcoulombs to coulombs. Now, the question A here says, calculate the initial electrostatic force between the spheres. Initial means before any movement is happening between them. Let's find out what the electrostatic force is between them. We know from Coulomb's law that the electrostatic force is given by K, Q1 times Q2, all divided by the square of the distance between them. Now, K is 9 by 10 to the power 9. Allow me not to put in the units in this case so that we don't get confused. And of course, you are allowed not to put in units when you are doing your calculations, but don't forget what you are calculating for so that at the end you are able to put in the appropriate unit for your quantity. In this case, the quantity we're calculating for is force, and therefore the resulting answer should have N, capital letter N, for newtons as the unit of force. Now, times Q1. Q1 is 2 microcoulombs, but we cannot use microcoulombs. We need to use coulombs. So we need to convert 2 microcoulombs to coulombs, and microcoulombs to coulombs we need to multiply by -6. That is micro. Times, open brackets, Q2. Q2, it's -6 microcoulombs. Now, I need to explain something here as well. You are not obliged to show the sign there, like I didn't show the sign here, the +2 for the first one. But remember, the plus and the minus, which are your charges, give you the direction of the force. You must remember that this is attraction. So you must be able to say at the end that the force is an attractive force, which is your direction. So allow me again not to show that sign. So this will be 6 by 10 to the power microcoulomb. Again, we are converting into coulombs, so we multiply by 6. Then this will be divided by r squared. Now let's look at r. R is the distance between the two spheres, and it's 100 millimeters. Now remember, milli, it's 10. If we were to convert the milli to the SI unit, we multiply by 10 to the power -3. So that 100 will be 100 by 10 to the power -3. But remember, this r, it's squared, and therefore you put it in brackets, and it's squared. Now I need a calculator to work out this now. So with a calculator, I'll then say this is 9 by 10 to the power 9 times 2 by 10 to the power -6 times 6 by 10 to the power -6. All this is divided by, I need a bracket because I'm going to square 100 by 10 to the power -3 squared. And now let's get to the answer. And the answer that I'm getting is 10.8 newtons. Now, I'm putting newtons because this is a force, and that is the unit for a force. But then another thing here is that we need to bring in direction because force is a vector quantity. Now, let's find out what's happening here. We have got a minus and a positive. These are positively charged and negatively charged particles that are hanged 100 millimeters away from each other. Definitely the force is such that this is attracted to Q1 and Q2 is attracted to Q1 is attracted to Q2 and Q2 is attracted to Q1. So just to say attraction would be enough to say that this force is such that the two charges are attracted to each other. Or you can say 10.8 newtons of Q2 towards Q1. Q2 towards Q1 or Q1 towards Q2. That would be enough. But the attraction is actually good enough to tell us the type of direction that these two spheres are going to take as they move. We know that attraction would mean they are moving towards each other. That's the direction. Let's move on to the next part of the question. It says, describe and explain the movement of the spheres. Oh, I've been actually doing that. Q1 will move towards Q2. And at the same time, Q2 will move towards Q1. Or you can sum it up and say Q1 and Q2 will move towards each other. That's all. You are saying there is attraction. That is the bottom line here. Let's move on to the next section of the question, which is number C. It says, calculate the charge on each sphere after they have touched. Now, these spheres are going to move towards each other because one is negatively charged, the other one is positively charged. So a force of attraction exists between them. They move towards each other. They come into contact with each other, and something is going to happen when they come into contact. Now, question C here wants us to calculate the resulting charge as the two spheres come to touch each other. Now, what we know is that when Q1 and Q2 come to actually touch each other, the charges on them is going to be distributed equally between them. So if we were to calculate the charge on each sphere after they have touched, it means we need to add the two charges together first and divide by 2 because we've got two spheres coming into contact with each other. So the charge, if you like, you can write charge. The resulting charge will be given by Q1 plus Q2, and we're going to divide by 2 because it's two spheres coming to meet each other or coming into contact with each other. If they were 3, we were going to use 3. Now, what is the charge on 1? The charge on 1 is 2 by 10 to the power minus 6, plus the charge on, this time the plus become very important. This is plus 2 by 10 to the power minus 6. This one is minus 6 by 10 to the power minus 6 coulombs. This should be divided by 2. Now, what will be the resulting charge here? Now, plus 2 minus 6 will be minus 4 by 10 to the power minus 6 divided by 2. Therefore, the resulting charge will be minus 4 divided by 2 will be minus 2 by 10 to the power minus 6 coulombs. That will be the charge on each sphere after the two spheres have come into contact with each other. Now, from question C going to question D builds on C. And please follow this carefully because this is likely to be in the exam. They like putting questions like this in the exam. So please understand how to work this out. So we have now worked out the charge on each sphere. It will be minus 2 by 10 to the power minus 6. Then question D says, calculate the number of electrons transferred. We know that it's electrons that can move, not protons. No. So not the positively charged particles are moving, but the negatively charged particles. Calculate the number of electrons transferred when the spheres are in contact. Now, for us to know the number of electrons transferred, we need to check what happened between the resulting charge and the previous charge. We can take maybe Q1 or Q2. Let's look at Q1. Q1 started with a charge of, so this is Q1. It started Q1. It started with a charge of plus 2 by 10 to minus 6. It is now at, so this is the new charge, minus 2 by 10 to the power minus 6 coulombs. Now, for us to know the number of electrons that moved this charge from there to there, we need to find the difference between these two charges and divide by the charge on an electron. So from there to there, we will then say, okay, let's find the difference between the two. The resulting charge is minus 2 by 10 to the power minus 6 minus the initial charge on Q1 was plus 2 by 10 to the power minus 6. So this gives us minus 2 minus 2, which is now minus 4 by 10 to the power minus 6. Now the minus 2 is this one. When we open the brackets here, this will become minus 2 by 10 to the power minus 6. Then you add the 2 together, it's minus 4 by 10 to the power minus 6. So that is what brought the difference in the charge of Q1. Now, if we want to know how many electrons caused this, we will say that the number of electrons that caused this will be this charge, minus 4 by 10 to the power minus 6, divided by the charge on an electron. Now, do you remember the charge on one electron? The charge on an electron is minus 1.6 by 10 to the power minus 19. Now, what number will this be? We again need our calculator to quickly get that. Now, I need a calculator to work out this problem here. Now, I've got minus 4 by 10 to minus 6 divided by minus 1.6 by 10 to minus 19. And that's the answer I get. The answer is saying I've got 2.5 by 10 to the power 13 electrons. Now, these are the number of electrons that were transferred from one particular sphere to another. So that was the number of electrons that were transferred. So we have answered that question. An interesting question indeed, and like I said, exam type of questions. You must know how to do this kind of calculations. So practice more from examples given in textbooks, previous question papers, work them out, and get used to solving this type of problems. Now, I want us to move on to one other section of our lesson, which talks about electric fields. What is an electric field? An electric field is a region in space around all charged objects in which a small positive test charge will experience a force. Now, it's a field in space, a region in space around a charged object where another charge, in this case we call it a small positive charge, a small positive test charge, will experience a force. Now, we do have different types of objects. You know, some objects are spherical, some are rectangular, you know, some are even irregular, okay? So we're going to look at particular types of objects, and they are going to give us a clue as to how electric fields are set up around them when they are charged. We will be talking about spheres, like in the example that I gave earlier on. We will be talking about parallel plates. So we choose our type of objects very carefully. We are going to look at how we represent these electric fields around them when they are charged. And firstly, allow me to talk about how to represent a field when we have a spherical object that is charged. Now here, we need to be careful. We know that we have got two types of charges. We can have a positive charge. So say this is our sphere and it is positively charged. Remember, we are saying that a field is a region in space. An electric field is a region in space around a charged object. So if this is my object that is charged, this region around it here, it would be my electric field due to that particular charged object. But for me to know that there is a field set up due to this charge here, I need to test it. And to test it, I need a small positive test charge, small positive Q. So if I put positive Q somewhere here, I can ask you this question. This charge here has set up a field around itself. If I put small positive Q there, in which direction do you think this small positive Q is going to move? Is it going to move away from this charge, or is it going to move towards this charge? Now, for us to answer that question, we need to go back to what we said earlier on, the repulsion between like charges and the attraction between unlike charges. So because this one is positively charged, and my charge here that has set up a field around itself is also positively charged, what will happen here is that there will be repulsion. And looking at Q, small q, because that is our test charge, small q is going to be repelled by this charge here, and it will be moving away from the charge. And the direction of the field, now this is important, the direction of the field is given by the direction of the small positive test charge. So the direction of the field is given by the direction of the small positive test charge. It's given by the small positive test charge. So if the test charge is going to move away from this charge, it means that I'm going to represent the field of this charge here in such a way that it also shows its direction, which is the direction that the positive test charge has taken when placed in that field. And now that the positive test charge is going to move away from the charge, the direction of the field will be actually the direction of the field will be shown as a line that shows that it is moving out of the positively charged sphere. Now, this line here that I have just drawn, and I've given it direction because I've put my test charge there, is called a field line. Now, we make use of field lines to represent the electric field around a charged sphere. Now, I'm going to talk more about the properties of electric field lines. But I'm drawing them now, and I'm also showing the direction of the field because the test charge has shown me in which direction the field is going. Now, I have represented the field around a positively charged sphere, making use of what we call field lines. Now, it is important for us to talk more about field lines, but before then, let me also put some negatively charged sphere here, because we had a positively charged sphere there. Now, the negatively charged sphere, in the same way, if I want to know in which direction is the field here, I'm going to put a small positively charged object there, which will be it will be my small positive test charge. It's positive. If I put a positively charged particle there in the field of this charge here, that small particle will move towards the charge because the positive and the negative will attract each other. So I expect that to happen. And the direction taken by my small positive test charge will be the direction of the field. So because the test charge will be moving towards my charged sphere here, that will be the direction of the field. And that will be the direction of the field. And like I said, we make use of field lines to represent an electric field. Remember that we cannot see an electric field by our naked eyes, and therefore we represent it using what we call field lines. And the direction I've shown there means that the field is moving into the negatively charged sphere. Now, you have heard me talking a lot about the direction of the field. Now, if a physical quantity has got direction, we classify it as a vector quantity. Now, definitely can have a magnitude of this electric field, and because we also talk direction, we can classify electric field here as a vector quantity. So in our list of vector quantities that we have started, you can then add electric field and say electric field is also a physical quantity with both magnitude and direction, because we know how the field is moving, either into the negative charge or out of the positive charge due to the direction we get from our positive test charge. Right, I want us to spend a few minutes talking about the field lines. And this will also explain to you why I draw the field lines the way I did. So let's talk about field lines. We have got properties of field lines. One is that they are perpendicular to the surface of the charged object. So you will see why I made it a point that as you look at my lines, they land on the charge at right angles, and they move out of the charge at right angles as well. I tried my best to show that. Now, we need to know that because we will be asked to represent field lines or show field lines from a charged object. They are perpendicular to the surface. Secondly, they never cross. Now you mustn't have this line here crossing that one. They don't cross each other. They are closer together where the field is stronger, and they are further apart where the field is weaker. Let's look at the section or this part here that talks about being close to each other and the field being strong in reference to our diagrams here. Now, if we look at the positively charged sphere, you would see that closer to the sphere, the field lines are more close to each other, and therefore we expect the field here at that point to be strong. In the same way, we can explain what happens as you move further away from the charge. As you move further away from the charge, look at what is happening. The distance between the field lines increases. So they are more far apart from each other on the periphery or in that part of your charged sphere or in that part of your field. So at this point here, we expect the field to be weaker because the field is weaker when the field lines are far apart from each other and much more strong where the field lines are closer to each other. So that is what is meant by that statement there. Let's come to the next one. The next one is actually what I have been explaining when we were looking for the direction of the field. The direction of the field or the direction of the field lines is always from the positively charged object to the negatively charged object. Now, this means that you will have your field lines radiating from positive. So radiates from positive to negative. So we can say that on the negatively charged sphere, field lines actually land there. They land there. We can go back to our diagrams and see that. You see the direction here for the field lines around the positively charged sphere are such that it's out of the sphere, the charged sphere. But for the negative, it's going in, so they land. They radiate from positive and land on the negative. So that's what we see happening there. The next property that we need to look at is that the direction at any point on the field line is the direction of the tangent to the field line at that point. The direction at any point on the field line is the direction of the tangent to the field line at that point. Now, a tangent is a line that just touches the surface of that line without crossing it. So the direction, that's why we could just show it right on the field lines, because the tangent to this line will be a line on it but not necessarily crossing it. In other words, if I were to bring in the second dimension to it, I wouldn't have the direction as going in that direction or this way. But it should be a tangent alongside that particular field line. Hence, we just put the arrow on top of the field line to show that direction. The number of lines is proportional to the magnitude of the charge. So the more field lines we have, the more big that charge is. The less field lines we have, the smaller that charge. These field lines surround a charged object three-dimensionally. This is very important. In other words, they radiate, these field lines are engulfing this charged object. You have got your X, your Y, and your Z. It's three-dimensional. So it's not like it's on that plane. You can only feel it from there, up there, and down here, but you can't feel it from this part. You can feel it from this part, and you can also feel it from the other part. So it's three-dimensional, like you would have a soccer ball, for example, as round as it is, if a charge is the center of that ball inside, that all around it would represent the field, which is the region around it. So it is three-dimensional. That is very important. You need to understand that. Field lines. Let's move on to look at what happens when we represent the field on spheres and when we represent field of parallel plates. Now that we have discussed the field lines, the properties of electric field lines, how we draw them, I think it is proper for us to move on to talk about the two types of electric fields that we have. One, we have a uniform field. Two, we also have non-uniform fields. Allow me to start with the non-uniform fields. And we have non-uniform fields when we talk about charged objects that are spherical. So for spherical charged objects, remember from the previous drawing we had of a sphere where we drew field lines. If this is a positively charged sphere, we know that the point charge that we're going to put in here, the positive point test charge, is going to be repelled by this charge, and therefore it will be moving away from the charge. And because it moves away from the charge, we will take that as the direction of the field, and therefore we're going to have field lines drawn that way and have the direction of the field line shown like that. That is away from the charge. Okay? Now, as we draw this, check again, and with reference from what we have already done in the previous diagram, see if we have a uniform or non-uniform field here. Now, referring back to the section we had on mechanics when we were talking uniform velocity, uniform acceleration. Remember, the word uniform means constant. So something is remaining the same throughout. Now, are we having uniform electric field here? We said yesterday that the distance between the field lines can tell us the strength of the field at any point. Now, if you are at a point here, this point is closer to the charge, and the distance between the field lines is that. But if I have a point somewhere there, the distance between the field lines this time is that. Now, the fact that the distances are not the same, it means that we are not going to have the same electric field throughout. At this point here, at this point there, we have a stronger electric field. The electric field is stronger there. But at this point here, the field is weaker. So in this way, since the field is not the same at each point or at any point around the charge, we say that here we have non-uniform electric field. So the electric field for spheres is non-uniform. It's not the same. Now for spheres, even if we have two or more of them in the field of each other, we will still have non-uniform electric field occurring between them. Say, for example, we have a positive sphere and a negative sphere. What is going to happen, we know that the field for a positive charge, the direction is away, and for a negative charge, the direction is into, or the field lines land on a negatively charged object. What we would have is something like this. Remember that they should start and land at 90 degrees. So please don't forget that. Trying so hard to get the 90-degree part done properly. So we would have this situation here. We'll have the field like that, or represented like that. The direction is, of course, from positive to negative. Now, if you look carefully at the field lines here, you can also realize that the field lines are such that we have the attraction shown between the positive and the negative. The attraction, which is the force, the electrostatic force existing between two charges that are not the same, plus and minus. In the same way, if we have the plus and a plus, what is going to happen? We should expect repulsion here, so we should expect things like that happening. So that will represent the repulsion. So your field lines are still 90 degrees on the sphere, but repulsion is being shown. You've got repulsion there. But don't forget as well your direction, the direction of the field lines. From the positive, it's out of the sphere. Okay, so they radiate out of the sphere in that way. Now, this indicates repulsion. But the same thing, again, the field is not the same throughout. The field at that point, it's not the same as the field at that point. So we don't have uniform field. Even here, we won't have uniform fields there because the distances between the field lines, it's not the same throughout. So we have non-uniform fields here. But then let's check and look at what happens when we have parallel plates. When we have parallel plates, let's see what happens to the field lines or the field between parallel plates. Now, if this is, say, positively charged and this is negatively charged, the two plates are oppositely charged. What is going to happen is that between the plates, we're going to have uniform electric field existing. Now, uniform electric field existing between the plates. So we'll have things like that representing the field. Now, for us to make sure that we're indicating uniform field, the distance between the field lines should be the same. I'm trying hard to do it in such a way that the distance between the field lines is the same. So the distance between the lines here is the same, and because of that we have what we call uniform field between the plates, between parallel plates. We have uniform field, and that's for parallel plates. Right. Now, the question is, what happens outside the plates? Outside here, the field becomes not uniform. So you've got a situation like that happening. It's not uniform outside the plates, but uniform inside the plates. Now, the direction is crucial. It's from positive to negative. Hence, you can see the direction over there. So we have, for parallel plates, we have uniform electric field for parallel plates. That's very important. Now, let's look at the electric field strength. Electric field strength at any point in space is defined as the force exerted on a tiny test charge divided by the magnitude of the test charge, divided by the magnitude of the test charge. And then, thus, then gives us the mathematical definition of what we're talking about. It's force divided by charge. And from this, we can deduce that the unit of this electric field strength will be Newton per Coulomb, because force is measured in newtons and charge in coulombs. Now let's look at an example here quickly. Example 3. A charge of 5 or plus 5 microcoulombs experiences a force of 0.012 newtons at a specific point in an electric field. Calculate the magnitude of the electric field at that point, the magnitude of the electric field strength. Now, when they say magnitude, this question is very deliberate. It tells you, you don't have to tell us the direction, you just have to tell us how big that electric field strength is. So from the formula given to us up there, electric field strength E is given by force divided by charge. And what will that be? We know that the force is 0.012 from what is given to us, divided by the charge. But hey, we are given the charge in microcoulombs. Remember to convert. Micro, you need to go to or convert it into coulombs by multiplying by 10 to the minus 6. Now I need a calculator quickly to work out the solution here, or the answer. So this will be 0.012 divided by 5 by 10 to the power minus 6. And what is the answer? It says that the electric field strength here is 2,400 newtons per coulomb. Okay, so that is our answer there. Let's then move on to this part here. We have looked at finding the electric field strength, making use of the test charge. So we bring in a test charge to any point around the field in that field created by a charge, and find the electric field strength using E equals F over Q. But then can we find the electric field strength of a charged object at any point around that field? The answer is yes. We can use this equation here, E equals KQ over R squared, which gives us the strength of the field at any point around the field. Now, for this equation here, we know that Q is the charge that creates the electric field. This time, it's not the small q. It's not the test charge. It's not that one. This time is the charge that creates the field. Sometimes we refer to it as the mother charge. And then the value of K, which is our constant, is 9 by 10 to the power 9 Newton meter squared per Coulomb squared. Now, let's have a look at an example. What is the electric field strength at a distance of 15 millimeters away from a charge of -5 microcoulombs? Now, we can use that equation. E equals K Q over R squared. Now, that would be equal to, we substitute into this, we know that K is 9 by 10 to the power 9. So we've substituted for K. And Q is what is given to us here, is -5. So we just look at the magnitude. That will be 5 microcoulombs. We know microcoulombs, you multiply by 10 to the power -6 to convert it into coulombs, divided by. Now, we also have 15 millimeters. Now, milli, remember, to convert milli to the right SI unit, we multiply that by 10 to the power -3. So that will be the conversions we have made. Now again, I need a calculator to quickly solve this problem. So that's 9 by 10 to the power 9 times 5 by 10 to -6 divided by 15 by 10 to -3. But this has to be squared because it's R squared there. So we need a calculator quickly to solve this. Now, we would then put in 9 by 10 to the power 9 times 5 by 10 to the power -6 divided by 15. I need to make sure here that I have my brackets on, because this is squared by 15 by 10 to the power -3, close brackets, squared. And let's see what the answer is. And we have got quite a huge answer there. Let me write it down in scientific notation. That will be 2 by 10. That will be 2 by 10 to the power, let's see how many zeros we have here. 1, 2, 3, 4, 5, 6, 7, 8. So that will be 2 by 10 to the power 8 newtons per coulomb. Remember that unit? Newtons per coulomb. So that is how we can use the formula E equals KQ over R squared to calculate the electric field strength at any point around that particular charge. Now, let's quickly come to finding electric field strength when we're looking at parallel plates. When we look at parallel plates, we check the potential difference across the plates. We also check the distance between the plates. And we use this formula here to calculate for the electric field strength between parallel plates. Now, remember, if you have your parallel plates, what I'm talking about is that there will be a potential difference across them, V there, across the plates. And these plates are a distance D apart. So this is where D comes from, and that is where V comes from. Now, if we calculate E using this formula, that will be V over D, V divided by D. You would see that the units we're going to use here is going to be volts per meter. So the units of measurement here will be volts per meter. Now, let me hasten to tell you that this is the unit that is usually or mainly preferred to the Newton per Coulomb. So when we calculate for electric fields, we're going to use this unit. which is volt per meter. Now let's have a look at how to find electric field strength when we have got parallel plates. Now, here is an example here. From what I've explained earlier on, I think we'll be able to solve this easily. We've got two plates, A and B. They are at distance D, 100 millimeters apart. And the potential difference between them is 2,000 volts. So V is 2,000 volts. And there is a small charge, -3 nanocoulombs, which is moving freely between the plates, and it moves from A to B under the influence of the electric field. Now, the question is, if we have got this small charge, which is -3 nanocoulomb, moving from A to B, which is the positive plate? Explain your answer. Now, this small charge here is positively charged. If it moves from A to B, it means A is repelling the -3 nanocoulomb charge, moving to B. So B should be positive and A should be negative. So which is the positive charge? The answer is it's plate B. So plate B is the one that is positively charged. Explain whether or not the charge will move with uniform acceleration between A and B. Consider only the effect of electric field strength. And of course, we'll say it will move with uniform acceleration because it is in a uniform field. In other words, it is experiencing the same force throughout. So that is the answer there. Now let's come to the calculation quickly. Calculate the magnitude and direction of the electrostatic force experienced by the charge as it moves between the plates. Now, remember that the force experienced by the charge will be given by the equation. Maybe let's start it there so that you understand what we're talking about. Remember this equation? So if we are to look for force there, it means force will be equal to EQ. Then now we need to find E because we know Q. Q is -3 nanocoulombs. So let's quickly find E. E is equal to potential difference divided by the distance between the plates. Now, what is the potential difference? Is 2,000 volts divided by the distance between the plates is given to us as 100 millimeters. So this will be 100 by 10 to -3 because I have to convert from millimeters to meters. And milli for conversion is 10 to the power -3. Now, we need to get an answer there. And for us to get that quickly, let's use our calculator. 2,000 volts divided by 100 by 10 to -3. And let's see what the electric field strength is. The electric field strength is 2 by 10 to the power. Let's get that answer carefully. It's 4 zeros, so by 10 to the power 4 volts per meter. Now, that's the most acceptable unit to use for electric field strength. Then the question is not telling us to calculate for the electric field strength, but it wants us to calculate for the force, okay, and the direction of the force as well. So F is equal to Q E from that formula there. 3 nanocoulombs. Nanocoulombs is 10 to the power -9, converting it into coulombs, times the electric field strength, 2 by 10 to the power 4. Okay, so that is what we have. And what is the answer? And once again, we need our calculator. 3 by 10 to the power -9 times 2 by 10 to the power 4. And let's see what the answer is here. We're going to have a force of 6 by 10 to the power. Need to get that answer carefully. So 1, 2, 3, 4, 5 to the power -5 newtons. And we also need to show the direction. The force is moving. We know that the positive one is B, so the force will be from B to A. From B to A. Why do we say so? Because we know that B is positive. Okay, so that is the solution to our problem there. Now, that brings us to the end of this lesson. I hope that you enjoyed it. And once again, let's meet the next time when we continue with lessons for grade 12. And I think this was actually the last revision session on grade 11 work. So from now on, the coming lessons will zoom straight on your grade 12 work. Thank you so much for watching. Goodbye.